everybody. It is 5 o'clock on Tuesday, so time for some Calc 3. As always, I know we had the mic issue last week, so let me know if any mic issues are coming up today. Hopefully it's working as it's supposed to. So we started chapter 13 or module 3 last week, and we started talking about multivariable functions, and we talked about limits. Now we start to really get into the interesting stuff and actually look at rates of change. The very first thing we're going to talk about are partial derivatives. And I'm not going to spend a ton of time on this topic. You guys saw the video lessons. There's a couple things I want to point out. And then we're going to talk about tangent planes. And then I'm going to have you guys practice taking some partial derivatives and then finding a tangent plane. So that's the plan for today and even part of Thursday. So with that said, let's get into partial derivatives. All right. Talk about what they are. Is everybody able to hear me, or am I coming in soft? Let's see. Okay, give me just a sec. Let's see. Give me just a sec. Let's see if we can turn up the microphone. Any better? You can't hear anything? Same? Okay. All right. Well, let's see what we can do about that. So I'm guessing you guys can hear me now. Is that a little better? Okay. Is it too loud? Or is this? Okay. All right. Cool. Great. Okay, good. Good. Thanks, guys. Sorry about that. All right. So let's talk about partial derivatives. So at this point, you guys are familiar with derivatives. You saw them in Calc 1 and got to use them again in Calc 2. And there's going to be a lot of overlap from what we did in those courses. But what we have to think about now is what happens when we have a multivariable function. All right. So for instance, here I've got a multivariable function, and this is like our level curves from last time. And so the level curves represent the monthly payment for any given loan amount and interest rate. So our input variables will be interest rate and loan amount. So if we were at about a 7.5 interest rate and a loan of $5,000, our payment would be $100 per month because we fall on that level curve. All right. Now, what we're going to look at with partial derivatives is if we hold one of the variables constant, what is our rate of change in the other direction? So in other words, let's say we hold our loan amount constant. Maybe we hold it at $3,000. A partial derivative would look at how our payment increases or decreases given a change in our interest rate. Or if we were to hold our interest rate constant, say at 11%, how does our payment change as our loan amount increases or decreases? So what we're doing with partial derivatives is we are specifically looking at the rate of change in one direction while holding the other direction constant. So we're not going to worry about, these are the definitions of partial derivatives. It should look familiar. It's a lot like the limit definition you learned way back when you first started derivatives. We're not going to spend any time on that in here, but these are what the definitions are. I'll talk a little bit about the notation too as we go forward. But what this would mean is this is a partial of f with respect to x at the point AB, okay? Or a partial with respect to y, so you have the subscript y at the point AB. Now here's our two main interpretations. We have a numerical interpretation, which is that instantaneous rate of change at the point AB, which means what happens with our function per unit increase in x with y held fixed, or vice versa. The change in y, if we're looking at f sub y, with x held fixed. Graphically, it's very similar to the graphical interpretation from Calc 1 because it does give us the slope of a tangent line at AB in the x direction, holding y constant, or in the y direction. We're not going to look at a plot just yet. We might look at one a little later. But it actually looks at the tangent line in a single direction. Now, here's the notations that we're going to see. We have the subscript notation that we saw before, or we could use this Leibniz notation that we've actually seen before in Calc 1. And this is a place where it becomes useful because we're taking the derivative of z with respect to x, or the derivative of z with respect to y. If we want to evaluate those partials at a point, we can plug in the point AB, and this is how we would do it. Going in and out. Has it been happening? Am I going in and out the whole time? Is everybody having trouble hearing me?
It just kind of sounds a little bit robotic, but I can tell what you're saying.
But so you're not having issues with it going in and out?
I can hear what you're saying, but it sounds kind of robotic. Like it is kind of like it waits, like the microphones wait to pick up sound. It's like kind of late on that. So I start to hear it a little bit late, kind of, yeah, choppy. There you go. It's a good way to put it.
Okay, let me see. All right. Let me take a quick look, see what's happening. All right, so again, what we were talking about, we talked a little bit about the numerical and the graphical representation, and we talked about the notations. So there's a couple other things I just want to show you. And number one is, first, let's just talk about determining the sign of a partial given a contour plot. So this would be our paraboloid here. And here's 4 different points where we have to determine the sign of the partials. Okay, so this is a nice exercise to try and get us starting to think in terms of partial derivatives. So we'll make a little table here. We'll have the points. And then we're going to determine the sign of f sub x and the sign of f sub y. All right. And we've got A, B, C, and D. And again, we're going to use what we know about instantaneous rates of change as well as stuff we've talked about previously. So let's say we're at this point A. All right, so we're right here at this point, and we want to determine the sign of the partial. So that would mean if we were to make a move in the positive x direction, so to the right, what would happen with the value of the function? Well, notice what's happening with the contours. This contour would be a line out here. This contour is a little lower, so it has a lower z value. So if we were moving to the right at point A, our z would be getting smaller, okay? So in other words, our function would be decreasing at A in the x direction. So that means we would expect our f sub x at A to be negative. All right. And one thing I want to emphasize, these are instantaneous rates of change, but what we're looking at is how does the z value change? How does the function value change as we move in the positive x direction for f sub x and positive y direction for f sub y. Now let's talk about moving this way for f sub y in the positive y direction. Remember what we said last time. If we move in a direction that is tangent to a level curve, then we expect to have no rate of change. Okay? So because it's an instantaneous rate of change, we would expect f sub y to approximately be 0 because we'd be moving in a direction tangent to the level curve if we're moving in the positive y direction at point A. Before we go on to the next one, I want to see if there's questions about either of those. All we're trying to do is get the sign, not how big they are or how small they are. But just like with tangent lines, the steeper, the larger the rate of change is, the more shallow, the smaller the rate of change is, or more negative. Okay. Now, point B, notice we'd be at the bottom of our paraboloid, right? So at the bottom of our paraboloid is going to be the one place where both of our partials are going to be 0, because again, it's an instantaneous rate of change. We talk about tangent lines a lot in Calc 1. Today, we're going to start to talk about tangent planes. Well, imagine a tangent plane to our paraboloid at 0, 0. It would basically be the xy plane, or the plane z equals 0. As when we get more into this next week, as we get into this next week, we're going to see some interesting stuff going on when both our partials are 0. All right, so at C, let's talk about it. F sub x, what do you guys think? Positive, negative, or 0? You guys got it. You're on it. What about f sub y, if we're trying to move in that positive y direction? Yep, good. Nice job, guys. All right, let's do D, f sub x. If we're moving to the right, and remember it's instantaneous. Very nice. And what about f sub y? Good. This can be a tricky one the first time you see it, but it's an instantaneous, so we would be going to a lower level curve if we were moving in that positive y direction. So that's going to be negative. So again, this exercise is just to try and get us some familiarity between level curves and our partial derivatives. Good work. All right. Guys, calculating these is simple if you are good with your derivative rules. All right. So for those of you guys who maybe haven't had any practice with your derivative rules in a little while, that might be something you want to do in the review activity or the review assignment in more, because that's going to be the key to doing your partial derivatives. What you do is you basically hold one variable constant and take a derivative with respect to the other. So I'm going to do one of these. I want to make sure I'm not going to do one that I'm going to give you guys here in a little bit. Let's see which. Let's see. All right. So I'm going to do a little bit on g of xy. Okay. Wanted to go through one with you so that you guys could ask questions if you had any. So we're going to do g of xy. We're going to do its first order partials, and then we'll come back and do its second order partials after we talk about those a little bit. All right. So g sub x, that's going to be the partial with respect to x. So this y here, I think of as a constant. It is going to take a little bit of getting used to the first time you guys do this, but once you get used to it, it's not that bad. So I see this whole y squared term as a constant, and that's how I'm going to treat it. So I'm taking the derivative with respect to x, and notice I've got a product, so this is going to be a product rule. So product rule, I'm going to leave the 3x squared alone times, oh, yep, and I did mean to do g, sorry. It is still a product rule, but I'm going to hold the y alone, y constant. Sorry, I'm going to do g. I'm going to give you guys h of xy. So I hold the 3x squared constant. This whole second part is what I'm going to take the derivative of, but y is just a constant. So what is that going to look like? Well, derivative of an exponential, so is itself times the derivative of its exponent, and then y is just a constant, so it ends up in my derivative. Now I'm going to hold this part constant, the e to the 2x y, and now I'm going to take the derivative of 3x squared, which is 6x. Now, one of the things that I would recommend on doing these is simplifying your first order partial, because that'll make it easier for your second order partial. So what I might do here, I can pull out a 3. Actually, I can pull out a 6, so that'll be nice. I can pull out an x, and I can pull out an e to the 2x. So I'm going to pull out 6x e to the 2x. And what does that leave me with? This term is just going to be left with a y. Oh, nope, an xy. Sorry, I missed that x there. Let me back that up a little. And maybe this won't be the best one to factor all the way out, just because, well, let's finish factoring it out and we'll take a look at it in a second. Actually, we can factor out the y too. Let's factor out that y as well, because both of them have a y in there. So we can actually factor out a 6 out of both, one of the x's out of both, an e to the 2x out of both, and a y out of both. So this is going to come out a lot nicer. That's better, because that just leaves us in the parentheses with one of those x's, and then we need a space holder for this guy, so +1. That'll make our second order partials a little bit easier to deal with. We might multiply the x back in just to save one of the product rules. So let's do that. So 6e to the 2x y times x squared plus x. So now when we do the second order with respect to x, come out a little cleaner.
Oh, I'm sorry, wait, what happened with the 3x squared?
Well, we factored a 3 and a 2, so that's the 6 out front, and we factored one of the x's out of here. So if I were to multiply this whole term back, the x squared is going to come from the x times x. The 6 is the 3 times 2.
I see it now. Gotcha.
Other questions on that one? Okay. I just got a notification that my internet connection is unstable. Can you guys still hear me? Okay. Everybody still hear me okay? All right. All right. So next, let's take a look. Choppy still? I mean, it may be, maybe it is the internet. I don't know why I'm having internet connections today, but apparently I am. Sorry, guys. We're going to keep trying to go through it, but keep me posted and let me know what's happening. Okay. Partial, let's do the partial with respect to y. This one actually works out pretty nice on this guy because there's only the one y term in here. So remember, this is all a constant. So the derivative of a constant times y is just the constant. So our partial is just going to be 3x squared e to the 2x times y. All right. Sorry, not times y. E to the y goes away because of the derivative. 3 times x squared e to the 2x. That is our derivative of g with respect to y. Those are what we call our first order partials, and with the interpretations we talked about previously. Now we also have second order partials. Those are second derivatives. Now there are two first order partials for a function of two variables. There are four second order partials for a function of two variables. Because we can take the derivative of x once again with respect to x. We can take the derivative of x with respect to y. We can take the derivative of the first order of y with respect to x and the first order of y with respect to y. So we end up with a lot of different variations. All right. I don't want to spend a ton of time going through these because I know you guys saw the video, but there is something we do want to see. So let's go through these, and I'm going to go through them a little quicker. So g sub xx, remember what that means. That means I'm doing the partial of g sub x, and x is my variable, which means y is my constant. All right. So that y, if it makes it easier, you can think of it being tied to this 6. And so once again, we have a product rule. So let me show you how you can think of this that might make it easier. The 6y is going to be in my final answer because those are both constants. Now I have e to the 2x times x squared plus x that I have to take the derivative of. So e to the 2x I'm going to leave alone, times the derivative of x squared plus x, which is 2x plus 1. Now I'm going to leave x squared plus x alone, times the derivative of e to the 2x, which we saw before, e to the 2x times 2. So there's our second order partial with respect to x. Yes, we could factor out the e to the 2x and write a polynomial in here. Because of time, I'm not going to worry about that right now because there's other things I want to make sure I show you first. But we could clean that up a little bit. Now, similarly, we have a g sub y. That is the derivative of g sub y, which is this guy with respect to y. There are no y's in here, so this is a constant. The derivative of a constant is 0. So the biggest thing you're going to have to get used to with partial derivatives is whichever variable you're taking the derivative with respect to, the other one you just think of as a constant. All right. Now we have what are called mixed ordered partials. So we have a g sub xy. So that's the derivative of g sub x, but this time with respect to y. So I go back up to here, and I need to do the derivative of this guy with respect to y. There's only the one y in here. Everything else is a constant. The derivative of y is 1. So I actually just get left with 6e to the 2x times x squared plus x. Now we have one other mixed order partial, g sub yx. And as you can imagine, now we're going to do g sub y with respect to x. So we're running the product rule on this guy here, because now we're doing the derivative of this with respect to x. So that's 3x squared left alone. Derivative of e to the 2x is e to the 2x times 2. Plus, now we're going to leave e to the 2x alone times 6x. Now, here's where things get really interesting for us. If I pull out the 6 and the e to the 2x, so there's the e to the 2x and there's the 6, 6e to the 2x. Look at what I get left with in parentheses. I get left with an x squared plus x. That is not a coincidence. You guys saw this in the video. If we did our derivatives correctly, our mixed order partials should come out equal, okay? And that should always happen. Now, I know I kind of ran through that quick, but I didn't want to spend a lot of time doing mixed order partials because I want to be able to make sure we have time later in class for you guys to do some. But I want to pause there and see if there's any questions about that. Okay, you guys are going to get to try one or two of these here in a little bit, but what I wanted to do was I actually want to go through 13.4 as a class first. That way, once we break into groups, you know, we don't have to come back together and meet. You guys can work on 13.3, and then if there's time, work on 13.4. All right? So, tangent planes and differentials. Now, we're familiar with tangent lines. You guys dealt with those in Calc 1 plenty, and even a little bit in Calc 2 with your first degree Taylor polynomials, right? So a lot of times you start off with local linearity. I'm going to go through this part a little quick. It's not that important for us right now, but we have a tangent line, right? And the tangent line is a good representation of our curve locally, but obviously as we get further apart, the two curves get further apart. As we zoom in, we see that the two become quite a bit alike. That's what the tangent line does. The tangent line represents our function locally. And our formula for the tangent line, if it's at 0, is b plus f prime of 0 times x, where f prime of 0 is our slope. All right, well, if we're doing it at 3 instead of 0, we just make a small adjustment. This should look familiar. This is a first order Taylor polynomial. You guys did those in Calc 2. Now, the reason I'm using this form is because all I need to find this is the function, its derivative, and the point that I'm finding the tangent line at. So the tangent line at x equals 3, or we could even generalize that at x equals, whoops, too far. At x equals a is f of a plus f prime of a times x minus a. All right, that's for any function. That's something you guys have done before. So let's talk about the relationship in 3 space, because we talked about planes before. Remember, a plane would be a constant plus m, which is our slope in the x direction, and n is which our slope in the y direction. Well, m is our partial with respect to x, and n is just our partial with respect to y. Okay? So we have one extra step for doing a tangent plane than we did a tangent line. And that is because we have a slope in the x direction and a slope in the y direction. So this will give us the formula for any tangent plane at the point AB. All right, so what we would do is we'd find our partials, f sub x and f sub y, input our point AB, that would give us our m and our n, and then we can build our tangent plane. So it's just an extension of what we were doing in 13.3. So hopefully you're seeing the similarities between Calc 1 and Calc 2, or excuse me, Calc 3. In Calc 1, you learned how to do derivatives. Then you learned how to use a derivative to find a tangent line. Now in Calc 3, we have partial derivatives, and we'll use partial derivatives to find a tangent plane. So here's a picture that I've always liked to kind of see what a tangent plane looks like. So here's the point of tangency. And what we're doing is we're taking the instantaneous change in the x direction times a change in the x direction, and an instantaneous change in the y direction plus the change in the y direction to estimate the change in the z direction. Now, the reason I bring this image up, I think a tangent plane we can get a pretty good idea of. You know, it's a plane that's tangent to our curve at a single point. Where this image really becomes useful is when we start to talk about a differential. So let me bring this over so we can have them both up at the same time. Okay, so here's the image here. And now let's talk about the differential. So the differential is the actual change represented in the tangent line. So in 2D, the differential is f prime, which is our slope, times our change in x. We're not going to do that one right now, but I want you to see where this is coming from. So before, let's make a nice connection here. So we talked about our tangent line having this form. You know, it had the form f of a plus f prime of a times x minus a. Okay? Now what the differential is this part right here. That's the differential. And what we have is f prime of a is our slope, that's our m, and x minus a is our change in x. So what's happening here with the differential is it's using our rate of change times our change in x to approximate the change in y. That's what the differential is. This, I'm having a hard time drawing a squiggly here. Let me try that again, sorry. This approximates our change in y. That's what a differential does. Now, let's think about why that might be useful. You know, you could say, well, right now I'm driving 25 miles an hour and I'm going to be driving for another 20 minutes. And you want to approximate how much further you're going to go in the next 20 minutes. Well, you would take your 25 miles an hour that you're going right now times your 20 minutes, which is a third of an hour. And so we could say that our distance, our change in y, is approximately going to be 25 thirds of a mile. So that should be an equals there. Okay, so that's what a differential does. It uses our instantaneous rate of change times our change in x to approximate the change in y. All right. Now, we know we might not be going 25 miles the whole time. And so the larger our change in x is, the larger our possible error in our change in y is. So again, These are only good locally. But a differential, that's what a differential does. So when we go into 3D, what a differential does, now the differential is this part of the tangent plane. So notice what we're doing is we're basically dropping off the f of AB. And we're replacing, let me write it in here. We're replacing the, come on. I don't know why that changed. We're replacing the x minus a with dx and the y minus b with dy.
Hey,
So
can you
that's
go
what
back
the
to the part where you
differential
were saying
is.
replacing?
Sorry?
Can you go back to the part where you're saying we're replacing? You cut out right after
Okay.
that. I think it's my internet connection though, instead is unstable.
I've already seen a thing that said mine is unstable, so I don't know what's going on today. What we're doing is essentially what the differential is it is the tangent plane, except we drop off the f of AB. So we have the f of AB here in the tangent plane. We're dropping that part off. So it's essentially this part of the tangent plane, except we're calling x minus a dx, and we're calling y minus b dy. Now the reason we're calling them that is because the differential is only a good approximation locally. So we only want to look at a small change in x and a small change in y. Because again, you can kind of see it from the curve here. The further we get out, the more this would be our error here. Sorry, that didn't write out very well. The distance here, there's our approximate from our differential or our tangent plane. There's the true value. That whole thing is the error. So the further we get away from our point, the bigger our error. So the bigger our dx and the bigger our dy, the more we can expect our approximation to be off by. All right. So that's why we use the dx notation and the dy notation. Plus it gives us a nice little quick shorthand notation for the differential. What I want you guys to take from this is what the differential is. The differential, again, is an approximation of the change in the function using our instantaneous rates of change, right? I gave you kind of the general example of if you're going 25 miles an hour for a third of an hour, roughly how much would you expect your distance to change by? It's the same idea, except now we've got a rate of change in both directions that we have to account for that contribute to our change in z value or our change in function value. All right. Questions about the differential? So again, what the differential does is, in general, it's just an approximation of our change in function value. In 2D, we do that with our derivative. In 3D, we do it with our partial derivatives. So it's basically using our rate of change in the x and y direction to approximate the combined change in the z direction. Let me get that writing off of there. So differentials, again, give us that expected change in our output given a change in input. Like we said, since these are estimates using an instantaneous rate of change, the larger the change in inputs, the less accurate our approximations will be. But that's what a differential is. The way you would do a differential in practice is you would find your partials at your point, and then your partial with respect to x would get multiplied by your change in x, your expected change in x. Your partial in the y direction would get multiplied by your change in the y direction. You'd add those together to get your approximate change in the z direction. Now, I don't want you to think of these as two different topics. The tangent plane and the differential are tied together because the differential is just, that didn't come out so well, is just this part here of the tangent plane. So the tangent plane becomes a plane by adding the constant onto it. Questions at this point?
So everything on that equation that you just highlighted, everything to the right of the f of AB is the two partial derivatives combined and the heights. And then you just add the constant at that point and you get it.
Yeah, okay. Basically. So it's almost like it's like you have to find the differential to get the tangent plane. Because you know, like I said, what you'll do in practice is you'll find your f sub x at AB and your f sub y at AB. Then if you're doing a differential, what it is, the only difference is how you use them. If you're doing a differential, you'll know your change in x and your change in y. And so you would multiply those by f sub x and f sub y, add them together, and that would approximate your, would approximate your change in z. Now, if you're doing a tangent plane, then you're actually looking for an equation. So you find your f sub x at AB, f sub y at AB, and f of AB, and then you just put together the equation of a plane. So they're two sides of the same coin, but we use them for different things. And there are times, if you know f of AB, that you can use the tangent plane to actually approximate your change in output value. Other questions? Okay. All right, I'm going to put the worksheets for 13.3 and 13.4 in chat. It's right here. Now for today, you know, all I'm worried about for today is getting through the worksheet on 13.3. If we need to save 13.4 for Thursday, that's fine because we only have one section for Thursday. So the big thing I want you working on in your groups today is working on just taking partial derivatives. And so I'm going to break you guys up into 3 groups, and I'll put these, I want you to try 2 of the partial derivatives, and you're going to get plenty of practice because you're going to find all 6 partial derivatives, the 2 first order and the 4 second order. And remember, the mixed partials should come out to be equal. Now, if you do get through the 2 partial derivative problems, then go on ahead and start to try 13.4 because you're just going to find a tangent plane. And once you can do partial derivatives, finding a tangent plane is actually pretty easy. So that's what we're going to do in the groups. And I just realized that all of that went into a private chat. Unbelievable. Sorry. I'm going to put the... There we go. Okay, so you got the links to the worksheets. I'll put them in when you guys are in groups too. Any questions about what you guys are doing for today? So 13.3 worksheet, you're going to do your partials. If you have finished early and you got time, then go on to 13.4. But the only one you're going to post for today's work is the 13.3 worksheet. All right, guys, welcome back. We only had a few minutes left, and I just wanted to say a couple things before we adjourn for the evening. Number one, like I said, the only worksheet to post for today's work is 13.3. If you didn't get to 13.4, no problem. We should have some time to work on that a little bit on Thursday. what I'm going to do on Thursday is I'm going to put you in the same groups. So that way, if you already started working on a certain problem, you can work on the same one. The other thing I wanted to mention, I've got the calendar up here just so you can kind of, so we're all looking at the same thing. Our midterm is scheduled for March 15th. Let me rephrase. The due date for the midterm is March 15th. Technically, that is during spring break, but I wanted to make sure you guys had enough time so that we would be able to have a review class on Thursday, enough time to get the homework done, the last quiz, if you wanted it. All that stuff can be done early, though. All right. So if you do have plans for break and you're worried about taking the midterm, then you can absolutely take it early. Okay. This is just when it has to be completed by. You got instructions right here for the midterm exam about how to sign up with ProctorU and sign up for the exam. So if you know when you want to take it, you guys can go ahead and do that. Just look out because they do charge an additional fee if you schedule within 72 hours of your exam taking time. And we want to avoid that. So once you have an account in ProctorU, you'll be able to find our Calculus 3 exam. You'll see it under my name, and it will have our course section number in it. The other thing I want to make sure I mention, as we've talked about before, the midterm take-home problems, you've gotten them for Module 1 and 2. Module 3 will be coming on Thursday, and those are due by the midterm. You can turn those in early, absolutely, but that's the final due date for those. Any questions about that, about the midterm? Review materials are available now in course contents. You can start to look over those. We'll talk about it more as it gets closer, but I wanted to spend a couple minutes just making sure you guys are aware of the dates.
Do we need a webcam for this?
Yes, you will need a webcam.
All right.
The proctoring will be done through ProctorU. You do need a webcam. The upside is, guys, you can schedule it whenever you want, 24/7 on your schedule, okay? But yes, you will need a webcam because that's how they proctor it.
So is ProctorU similar to RP now, or is it like someone watches you take the test?
Somebody will watch you take somebody watches you take the exam. So it's a live proctor, and they have you share your screen. So that's how they ensure that people aren't going out to other websites.
What exactly are we allowed to use on the exam other than a calculator?
Two 3x5 note cards, both sides.
Is there a setup like there was for lockdown, or is it you just go into the website and it pretty much sets you up for it?
Yeah, it won't be like it won't be as annoying as Lockdown browser. You do have to go into ProctorU to create an account, but that part is pretty quick. And after that, you can schedule. And then when you schedule, it's actually kind of like what we do with a Zoom call. The proctor will say, okay, I need you to share your screen and your webcam, and then they'll put in the password for the exam for you, and you'll actually take it right in more.
Okay.
Yeah, it's going to be a lot less. It's going to be a lot less stressful than Respondus.
Yeah, I don't need it locking down halfway through the exam like last semester.
Oh, trust me. I'm so glad that we've got ProctorU for this semester. It's such a better option. All right. So, well, yeah, I understand, Cooper. Me too. Trust me. Oh, man, it was not fun. But yeah, ProctorU is a much better option. The nice part is, you guys can schedule it when you want. we don't have to try and meet for a class, and it gives us that Thursday, gosh, what's the date? That Thursday, the 11th, that class will be completely open so that if people have questions, you can ask questions, or if you want to use that time to study or work on take-home problems, you can. So, you know, it's not a perfect option by any means, but it's definitely better than Respondus. So, but yeah, guys, if you have any questions between now and Thursday, as always, shoot me an email. Don't forget, you got online tutoring and the forum if you have questions on problems. So make sure you take advantage of those as needed. We'll pick up with 13.5 on Thursday, and we'll finish off the 13.4 worksheet and the 13.5 worksheet. All right. All right, guys, have a good night. I'll get the stuff from today posted in more tonight.